Okay, so in this video, we'll talk about Korselt's criterion. So first of all, we recall what a Carmichael number is. So a Carmichael number is a composite number n such that the congruence a to the n is congruent to a mod n holds for every integer a. So we had seen in a previous video that 561 is a Carmichael number. So now we state Korselt's criterion. So Korselt's criterion says that a square free number n is a Carmichael number if and only if p minus 1 divides n minus 1 for every prime factor p of n. Okay, so we prove the sufficiency first. So proof. So since n is assumed to be square free, we write its prime factorization as p1, p2, pr, where p1, p2, pr are prime factors. So let's choose any one of these primes, say pi, where I is between 1 and r. And we have phi of pi equals pi minus 1, where we recall that phi is Euler's phi function, which counts how many positive integers are less than or equal to pi and prime to it. So by hypothesis, we have pi minus 1 divides n minus 1, and we can rewrite this as n is congruent to 1 mod phi of pi. So by Euclidean division, we can write n as k times phi of pi plus 1 for some integer k. So now, if we make use of Fermat's little theorem, we have a to the phi of pi is congruent to 1 mod pi for every integer a. So we have made use of Fermat's little theorem. So it follows that a to the k times phi of pi is congruent to 1 mod pi, and therefore a to the n is congruent to a mod pi. So a to the n is congruent to a mod p1, p2, pr, because each of these factors are pairwise coprime, and that's just n. So a to the n is congruent to a mod n. So n is indeed a Carmichael number. So that was the proof of the sufficiency. So now we'll prove the necessity condition. So now we have to assume that n is square free and Carmichael. So again, we write n as p1, p2, pr, where these are the different prime factors of n, and we'll assume that n is Carmichael, meaning that a to the n is congruent to a modulo n for all integers a. So in particular, we have a to the n is congruent to a mod pi for any one of these prime factors. So since this is true for every integer a, this must be true even if a is a primitive root of pi. So we recall that a primitive root is just a generator of z modulo pi z star. So we must have n is congruent to 1 modulo pi, and that completes the necessity proof. So now, as an easy exercise, use Korselt's criterion to show that a Carmichael number is necessarily odd. Okay. So now we'll have a look at how to use Korselt's criterion to prove an observation due to Chernick, which says that the number 6k plus 1 times 12k plus 1 times 18k plus 1 is a Carmichael number if each of these factors is prime. So that can be proved easily using Korselt's criterion. So we suppose that n is equal to 6k plus 1, 12k plus 1, times 18k plus 1. And we suppose that each of these is prime. Okay, so that forms a prime triplet. So then n is square free. No two of these primes are equal. So n is square free. And if we expand this out, we obtain n minus 1 is equal to 6k plus 1 times. And if we expand this out, we obtain plus 18 squared times k squared plus 2 times 18k. All right. So now if you look carefully, each of these is divisible by 6k, 12k, and 18k. So by Korselt's criterion, n is then a Carmichael number.